In the earlier lecture, what we saw? We saw the vector operations. Okay, we saw main thing what we saw is the vector additions. Correct? And we saw initially we saw a scalar, multiplication of scalar with a vector. That's okay, that is simpler, trivial. And what we saw is a vector addition, which is important. Vector addition can be described by two laws. Correct. So first one is what? Triangle law. Triangle law. And another one is parallelogram law. Actually, in fact, both the laws are same. Okay. So this is just a convenience, how you can add up. Whichever the way you can add it, you can use it up. Okay, so what we saw in a triangle law, how did we add? So if we have two vectors, say something like this, one vector and another vector, the same direction. Okay, then the resultant of these two vectors will be a single vector. Okay, so if you represent a vector, this I call it as A, and this is B, and the vector A is defined by the direction and the magnitude, the length. Then the resultant vector C will be nothing but C vector equal to A vector plus B vector. It can be represented in the form of a triangle. Okay, so you join these two vectors edge points. So this is the magnitude of the vector, and this will be direction of the vector. So similarly, we did for the parallelogram law. Parallelogram law, what happened if you connect two vectors? If they had what is the vector? This is the tail and this is the head, correct? If you join the tail of two vectors and the resultant vector will be in which direction? Along this direction. And how can you construct it? Draw a parallelogram. Okay. So now tell me, okay, so this is a vector, right? I have put drawing, this is a vector and this is a vector. So let us call this as A vector, B vector, and this is a C vector. Okay. So remember, we are representing not just by direction as well as magnitude. Magnitude is the length of the vector line. Okay. Length of this ray that defines the magnitude of the vector. And okay, so let me call this as D vector and this is E vector. Can you tell me what are the equal vectors here? Equal vector. Equal vectors means they should be equal in magnitude, only same direction? Yes, equal vector should be, the first definition is that you have to read all those definitions. Equal vector means they should be equal in magnitude as well as the direction. Can you tell me what are the equal vectors here?
B vector, D vector, and A vector and
E vector. Okay, so this is the way you can. So any vector can be, so vector means it says only a direction and the magnitude. You can draw wherever you want. Okay, why do we do all this? Why do we need this addition of vectors? Why do we, and here we saw, right? So yesterday I think we wrote it as PQR or something like that. So if you remember, we wrote the magnitude of the vector, the resultant C. If you remember, the magnitude is what? Can you tell me what is the magnitude C? C square will be equal to some A square plus B square plus 2AB cos theta. Okay, but theta is what? Theta is the angle between the vector A and B. This is simple to prove. And we did the angle also, right? So what was that? Tan alpha we had, right? So what is the tan alpha? Suppose if the angle between this vector, if I call this as alpha. So tan alpha will be equal to, tell me. So here I don't have A, correct? So this will be, yeah, correct. A vector divided by B vector plus A cos theta. Sorry, magnitude this one. Okay? So this is the way the angle is also defined. Am I right? Yes, that's right. Because A sine theta this is. We have proved yesterday, correct? So, because if you remember how we proved, we took a line here, top this is the angle theta, and then we know that tan alpha will be, so if I call it as say some P, Q, R, S or something, so what we had, tan alpha will be equal to what? Opposite side RS divided by PS, correct? So, PS is what? RS is what? RS is this vector, correct? This sine theta, right? RS will be, so what happened? Your sine theta will be RS divided by QR. QR is nothing but a vector, correct? Therefore, RS will be A sine theta. So, therefore, this becomes A sine theta. Okay, and what is PS? PS is equal to PQ plus QS. So, that is PQ plus QS. So, what is PQ? PQ is nothing but B. So, PQ became B. And what is QS? This is the A sine theta. Sorry, A cos theta. A cos theta. And that's what we got it here. Okay. So, this is the way the means addition of vectors are being done. Okay. And why do we need to do this? Why do we need to add two vectors? Why do we need to, means in a real problem, in a real life problem where what's some problem? Okay, let us take out the same problem, what we are used to see. There is a catapult, right? So what are you doing catapult? So we are having a catapult with a string stretched. Okay. So this is a string, am I right? So this will be the Y-shaped rod. Okay, and you are going to have a stone here. When you leave it, the stone goes, right? So I will remove this. So this is the top view of the catapult we are seeing. Now I am asking, so, and if what are the forces acting? So we have three forces. One force which I am going to hold it by the hand. Am I right? So that's the one force. Till then I am holding by the hand, the stone will be there only. Because there are three forces acting, correct? 1, 2 and 3. So let me call it as F1 and F2. So now these are all vectors. Okay, so now when I leave this stone, leave this hand, so then there will be a force which is going to act on this stone, which is going to make the stone move along a direction, correct? So let me call that as F3. This is a simple problem. So now what I am asking, so I don't know which direction it is going. I say I don't know the direction. So I given you these two vectors. This is a simple problem. Now you can say, okay, the direction will be here. So even a simple problem, suppose but you don't know. F1 is not equal to F2. If F1 is equal to F2, you know it goes straight, correct? If F1 is not equal to F2, if you are not able to pull it properly, then it's not going to go straight, go some other direction. I'm asking what will be the direction and what will be the magnitude. So then we have to do you can use a parallelogram or you can use your, means the direction you can get it from the triangle also. So what you have to do, we have to first represent this F1 and F2 by, in the vector diagram. Okay. So let us write F1 as how the F1 look like. Let me form a triangle. Okay. So how do you, if you want to use a triangle law, they should be A vector and B vector should be in the same direction, means it should be same sense, cyclic or anticyclic, and this will be opposite, right? So now here you can't, this is opposite sense, na? So if you move it here, then you can draw. So what happened? We are having, let me draw one vector. So this represents, let this represent your F1 in terms of direction as well as magnitude. Always remember direction as well as magnitude. So now, so this is something parallel to it. So I wanted to make an equal vector of this. So then what will happen? So I will draw something from here I will draw. Okay, so this will be what? F2. So it's a direction as well as magnitude. So now my triangle law says if you have this is the vector where the vector is in the same sense, when you add up two vectors on same sense, the resultant vector will be just finish the triangle. Correct? You just finish the triangle here. Okay, so and this is going to be the real resultant vector F3. So then you can draw. So this is the F3. So this will be the direction and the length will be something like F3. Okay, so this is the way, this is why we use the vector addition is required for us to find out the resultant, what is that? Resultant vectors. And now if you ask me what is the magnitude, okay, of course you can draw the triangle and find out what is the magnitude also. So you can find out the magnitude, for finding the magnitude again you can use the same thing, parallelogram law and direction. What does the parallelogram law says? See, already you formed. What the parallelogram says? If both the vectors, if the tails are coincident, here already the tail is coincident. All you have to do is construct a parallelogram. Okay, and parallelogram, then the diagonal is the magnitude of the vector F3. Okay, so now can you tell me what is the magnitude of the vector F3? Very good, correct. What is that? Very good. F3 square will be equal to F1 square plus F2 square plus 2 F1, F2 and cos theta. What is theta? Theta is the angle between these two vectors. Okay. So now, so you can see, and this gives you a lot of things. Okay, so what happened? Suppose if you are pulling this stone far away, what will happen to the angle? Become smaller or smaller? So what it says, when you pull the catapult long and if you leave, will get a more force or less force? When you leave it?
The distance will increase.
Correct. That means what? The force you are applying is larger. Correct. Of course, because when you pull it farther, it goes. When you pull, the theta decreases. Correct. So when the theta decreases, increases. Cos 0 equal to 1. Correct. Cos theta will reaches 1. So that's what your force will also increase. You got it? So what it says is, you have the same magnitude vector. So a magnitude vector, not a direction. Same magnitude vector. So I'll have this F1 and another one vector F2. Okay. The resultant vector will be along this line. Correct? Along this line. Maybe that's how you're going to do. You finish up the parallelogram and get it. Okay. Now, this resultant vector, the magnitude will increase the moment if this angle between the vectors, as it becomes smaller, same magnitude, but the angle I am going to reduce. Okay, so then what happened? Your parallelogram will be something like this. Okay, so then your vector magnitude will increase. You got it? And that's what saying from here. Even the F1, F2 is same. As you reduce the theta, your F3 magnitude will keep increasing. Okay. So this is the reason. And angle formula, you know what is the angle and all, you can find out the angle, you can get it from those formulas. Okay. So this is the reason why we need to know this vector addition to find out when you have many vectors. For example, a simple problem of catapult. So what will be the resultant direction? Or you have a bow and arrow. Okay. Or you are pulling a tug of war. So many things. Anywhere else you will have a different, when you are raising a pole. Have you seen the people raising and fixing a pole? They tie different ropes and pull it, right? So where you want to say what is the resultant motion? Then you have to take all this triangle of vectors. Okay. So they are all vector additions. So that's why you need to know the, what happened? The vector addition is important. Okay. So, and of course, nobody who is going to raise the pole is not going to calculate the vector and do. They themselves, by the experience, they will do. They are not going to do the vector addition. We will do it. Physics people will do it. Fine. Okay, now the interesting thing is, okay, what is interesting thing is here, okay, so this parallelogram law says, if you have any two vector, the result that two vector or two different vector can be represented by a single resultant vector. Now the same way, then I can tell, if you give me any vector, that also can be expressed as a two vectors. You got it? So that means what I am going to resolve the vectors. Okay, and in fact, if you remember, we had let me go by the triangle law. So I am going to have another triangle law of something like that. If you remember, we did while proving this associative law, we took three vectors. Correct? So then what happened? So let me call this as A vector, B vector, C vector. Okay. So the resultant vector will be
A vector plus B vector plus
A vector plus B vector plus C
C vector.
vector, and that we can put it anyway in the bracket, whatever you can. So you associate it. So we'll call this as a R vector or something. So what it says is, a combination of all these vectors can be represented by a single vector. Or other hand, or I can invert the problem and say any single vector can be represented as a combination of many vectors. Okay. So for example, what am I going to do? So let us take it. So let us take the same problem. So your R vector can be written as, if I give you R vector, that can be written as A vector plus B vector plus C vector. So let me call the unit vector, if there is a unit vector, we call it as UA cap, UB cap and UC cap. Okay, so then what happened? Then you can write this as A UA cap plus B UB cap plus C UC cap. Okay, so you can, and this will be your R vector. If I want to write R vector will be what? So R vector will have this direction. So then you have resolved this vector R into three different vectors. And this is very important. Okay, why this is important is, okay, so the process of splitting a given vector into its components is called as the resolution of the vector. Okay, and why this resolving a vector is important? Why do we need to do? I said, why do you want to add the vector? Because to find out the resultant direction. Now I ask you a real problem, in some problem, why do you want to resolve a vector? Okay, a very simple and easy problem is, there's a boy standing on the ground, and so this is the ground, and there's a boy standing here. Okay, he is throwing a stone. What is doing? He is going to throw a stone. So at a certain angle. Okay, what happened? The stone will move on like this and go and fall down. Correct? So now if you see this problem, so the stone is going to move from here and going to fall down. Now I'm asking you, what is the maximum height the stone has reached? Correct. Of course, from the figure you can say the number. And what is the maximum distance it has reached? What do you do? How do you do? What will you do is, so this is the vector, initial vector, which is throwing. Resolve the vector into two components. Okay, let me call this as, suppose if he is throwing at initial velocity v, this will be Vx and Vy. Correct? So then when I forget about Vx, I will just see Vx. So this will be what? This will be equivalent to, if a guy is throwing a stone upwards at a velocity Vy. What is the height it go? It will go certain height and come back. That will be the same height because that is a component of the velocity. So if I consider, if the boy is throwing a stone vertically upwards at a velocity Vy, which I have resolved it. So then it gives me the height, at what is the height it has reached. And same way, If he is throwing horizontally, of course, anyway, always is make a parabolic path. Okay, so it's something like that. If it is, this is the velocity. Okay, what is the horizontal distance? That also, for to get the horizontal distance, this Vx will give me an idea. What is the horizontal distance? It has, the stone has moved on. Okay, so how long it moves on? Whenever the Vx will be, it keeps on going until this Vy pulls back and hits on the ground. Okay, so it will have a combination of Vy also will be there. So no need to bother about it. So for these types of problems, there are many other problems. A given vector should be always resolved into two components, and then it will be easy. And when you resolve them into two perpendicular, this is a perpendicular component. Na? What you have done is perpendicular, right? One is up and one is downwards. We have resolved a vector into two perpendicular components, and then we call that called as a rectangular components. So this division of vector into two perpendicular component is called as your rectangular components. Okay, so, and this is important. And how do we, if you remember in the first class when we defining about the unit vectors, we defined a notation. Unit vector along the x-axis is I cap, y-axis is j cap, and z-axis is k cap. Okay, so then we can always resolve a vector into three different components. Okay, this I am drawing in a 2D, in a space. In a 3 dimension, if this is the velocity, this velocity can be resolved into x direction, Vx, Vy and Vz. So your Vx will be sum of all these three. And that's what a triangle and everything is coming up. Got it? So you can visualize what is happening. We have done it. So, and now how we are going to do it? Okay, so if you wanted to see that, I can tell you what is that. Okay, so then, okay, so what we are doing? So we are having x-axis and y-axis. Sorry, x-axis and y-axis. Okay, suppose if this is the vector. Okay, and what am I going to do? Let me resolve the vector. So there will be a, if I take a projection on this one, so what happens? So you will have a vector like this here. Let me call it as R. So what am I going to do? So I want to take a, I want to take this, okay, let us take 2 dimension. Let us not go into the 3 dimension first case, 2 dimension I am going to take. So we are having R vector. So you are having a vector in this direction. Now we wanted to resolve this vector into along the x component and the y component. Can you tell me what will be the x component? Suppose if this angle is theta, so this will be r cos theta, and this will be r sin theta. So this will be r sin theta, correct? So therefore, so your r vector, you are resolving into rx plus ry. Am I right? And rx vector will be equal to r cos theta, and the direction is x-axis, unit vector along the x, correct? And ry will be equal to r sin theta, and that will be along ij cap, correct? Because this direction is called as your I cap and this is your j cap. Okay. So now can you tell me what will be your, okay, so let me take out the magnitude. So Rx will be what? R cos theta, and Ry will be R sin theta. So what is Rx square plus Ry square? R or R square? Why? This is what? R square cos square theta plus R square sin square theta. That will become what? R square. Okay. So this gives you, and can you compare? So this gives a magnitude of the R. So the R vector can be represented as in terms of Rx and Ry. After resolving, this is the property you have to do. So now can you compare this equation, are they same? Parallelogram law.
No,
Is this a parallelogram?
it is the parallelogram.
Okay. So tell me, what is that equation saying?
Okay, no, if that one has cos, this is in this parallelogram the theta is 90 degrees, so cos theta will be 0.
That's it. Cos theta will be 0. So it's the same formula.
Ah.
Okay. That's the same. That's why we are using, that's why I said this is, we are using the same formula to resolve a vector into two different components.
Ah.
Okay. So that's what we have to see in this. And okay, that's the same thing. And same thing you can use angle also. What will be the angle? Theta, tell me.
That theta will be 45 degrees.
Which angle? This is not 45 degree. How can it be 45 degree?
You say theta.
Theta. Why it will be 45 degree?
Oh, it would be half.
It won't be off. Why will I make it a vector? So if I give you a vector like this, it won't be 45 degree. Now you have to give me what will be the angle? Okay, this is R vector. So this is Rx, Ry. Rx equal to R cos theta, Ry equal to R sin theta. That's the magnitude. Okay, and what we found, R square equal to Rx square plus Ry square. Tell me what will be this angle? This angle we gave, na, theta equal to sin theta by cos theta, that you can always find it out. Okay. You got it, now? What is that? How will you find out? Take the tan theta. What is tan theta? Take the, okay, what are you having? Rx equal to R cos theta, Ry will be equal to R sin theta. Take the ratio of these two. These two? So what happened?
Cos theta.
Ry by Rx will be
Cos theta.
tan theta.
Oh, R, huh.
Correct? So this is the way. So your angle is connected to this gives you how your Rx component, Ry component are connected to the angle with the x vector. Okay, and that's what they have. Okay, this is what we have done for, okay, so this is important. Okay, this is how we resolve a vector. So we, in physics problem when you are dealing, you have to get, when given two vectors, you want to get what is the resultant vector also. And there are sometimes the problems it demands, given a vector, you need to resolve them into two different components also. So by this parallelogram law and everything, we can actually resolve a vector, we can get the resultant vector as well as we can resolve a vector also. Okay, so this is how we resolve the vector. And the important thing is, this is what I draw. Okay, this is x and this is y. So this direction will be I cap, this will be j cap. Okay, so if you can actually do it for the 3 dimension also when you have in z. Okay, so suppose if I had a 3rd dimension like this coming perpendicularly out of the board from this point, and if I have a vector like this, so what I do, first I take either the projection on one vector. Okay, projection on, it means you put a torchlight vertically along the z-axis. It's going to form a shadow. So that will be the magnitude of this vector on this plane. Am I making it clear? Okay, let me explain you more better. Okay, fine. So as I told, any vector can be resolved into any combination of vectors. Okay, so let us see how am I going to, this is only 2 dimension is simple. So how am I going to do it on a 3 dimension? So let us see. Anyway, you don't have it in the book, they just directly written that. So let me explain how we can resolve it in a 3-dimension. Okay, so let me use some different colors. So let me draw the axis. This is your, let me call, okay, you want to call it as y-axis you want to call, okay, fine. And this will be your x-axis and a perpendicular to here. This is z-axis, okay. These all are perpendicular. Okay, these all are perpendicular to each other. Can you make it clear now? This is clear? So this is a 3-dimension. I can't, this, what z is actually, this is coming like this. I am drawing like this. Okay, how do we draw a box? We draw a box like this. Okay, in a cubic box, what will you draw? Okay, that way I have drawn it. Okay, so this is one. So when I do, so this is the axis, how we draw. Correct? That's what I have drawn here. Okay, so now I am giving a vector, let us say a vector be this, in this direction. So now this is a plane. So I can resolve this vector into 2 components. One is along this line somewhere else, another one is along this y-axis. Correct? So then what I am going to do, so let me draw that vector. So this is the r vector, okay. It will have a component. If I take the projection, it is going to fall like this. Correct? This is the shadow of the vector on this zx plane. This is a plane, zx plane, and there will be one more component along this one. Am I right? So then you can call, so what is the unit vector for here? I cap, j cap and k cap. So now, so this projection, I can write this as ry. Okay, and this I am going to call as, this is falling on rxz. So I will call it as rxz. You can find out the values also, correct? Because if I call this as theta, so then this is ry will be r cos theta and rxz equal to r sin theta, correct? So now this vector is on the plane yz. This can also be resolved. So if I call this angle as theta alpha, so then what happens? This will be, so okay, from here what happens? So ry will be what? So ry will be r cos theta. And this will be rxz will be, tell me what it will be? Yeah, r sin theta, correct? Am I right? So now this rx vector, this also can be resolved along the x-axis, because then you see only this plane on the floor. Suppose this is the floor. Okay, this can be resolved along this x-axis and y-axis, correct? Z-axis, correct. So then what I am going to call this resolved along the x-axis, I am going to call it as rx, and along the z-axis I am going to call it as rz. Okay, so and let us give us given the angle, this is alpha, correct? So this will be what? If this is r, so let us draw this figure separately. Okay, so what am I going to have? We are having something like, I am going to have rx, I am going to have rx here, okay, rx here, and this is rxz, and this angle is alpha, and then this line, correct? This is rx, this is rxz, and this is rz, this is alpha, and this is the way we can resolve this into 2 components. Am I right? So this will be what? Rx will be rxz cos alpha.
Cos.
Cos alpha. Okay, because always the line which is going to the cos, we saw earlier, right? And RZ will be what? RXZ sin alpha. So then what happened? Now you have resolved a vector R into along the x component, y component and z component. So now let us write down the vector. So your Rx component will be Rx component is what? Rxz cos alpha, and now you know Rxz. Okay, so that will be what? R sin theta, correct? Rxz is R sin theta. Sin theta cos alpha. Okay, and now you tell me what will be Ry. Okay, Ry is already we given. What will be Rz?
Rxz sin alpha.
Okay, Rxz sin alpha. What is Rxz? R sin alpha, correct? So this will be R sin alpha of sin theta sin alpha, correct? Now, this is a trigonometry problem. I am asking you, what will be your Rx square plus Ry square plus Rz square? Correct? So you have to take Rx square is R square sin square theta cos square alpha. Okay? So what it will be, tell me? R square
sin square theta
cos square alpha. Correct? Plus Ry square. What is that? R square cos square theta. Correct? Plus Rz square. Plus Rz square is what? R square sin square theta sin square alpha. What this will be? Combine these two. What will you have? R square sin square theta into cos square alpha plus sin square alpha. That is 1. Okay. So therefore this becomes R sin square theta, and this will be plus R square cos square theta. That will be R square. You got it? So earlier, if you remember what the relation we wrote here, c square for two vectors, c square equal to a square plus b square. Means when you resolve this vector into orthogonal components, okay, perpendicular. When this resolve into two perpendicular components, if you resolve them into two perpendicular components, that will be the magnitude square will be square of sum of these two squares. Similarly, when I resolve it into three components, so what am I doing? I am actually resolving every vector. Given a vector, if I resolve into two component, then the magnitude r square will be rx square plus ry square. If I resolve into three components, there will be rx square plus ry square plus rz square. Okay, and what is the condition when it will happen? When those axes are perpendicular to each other. What they call, this is typically what you call as a orthogonal. Okay, so now you can see this is a property. So in advanced classes, you will see, in fact, there not need to be three. There can be many axes. Now you can see how you are going to draw many axes perpendicular to. You got it? It's a three-dimensional space. We live in a three-dimensional space where your x, y and z is there. They all are perpendicular to each other. Suppose you have a different dimensions where you can define many vectors which are perpendicular to each other. So then any vector, given any vector, the magnitude of the vector can be written as the sum of all these components, square of the components. Okay, so this is what. So why we are saying this is, in a 2-dimension, it will be rx square plus ry square. In a 3-dimension, r square will be equal to rx square plus ry square plus rz square. If you can keep on increasing your dimension, that square term will keep on increasing. Okay, so this is one of the interesting property of resolving the vectors. Okay, and okay, Okay, there's a one simple thing that's not very important. Okay, what they say is, if you have two vectors, two equal vectors, okay, two vectors are equal. When you resolve it into three components. So what you are having, we are having a vector, A vector is equal to B vector. So let me resolve this A vector into three dimension, x, y, z. So then what I am going to have, let me call A vector be equal to, okay, let us say, good, Ax I cap plus Ay,
I cap. It will be square. Square of those.
that is a magnitude. How do you resolve a vector? Triangle law.
Okay.
A vector, B vector, C vector, correct? C vector equal to what? A vector plus B vector, okay? Okay, so now I am giving you two vectors. This is a x, correct? Y, I am giving you a vector. Tell me. So this is a vector, correct? So what this will be? This will be Ax I cap, correct? And this will be Ay j cap, correct? So then if I draw a vector here, so this vector direction will be like this, correct? If I draw a vector here, what that vector will be? This vector direction is like this, correct? This will be same equal vector. So A y j cap. Now try to use a triangle law. Can you use a triangle law? So A vector will be equal to Ax I cap plus Ay j cap. Same I do it here. Okay. So what happened? Try it out. Your R vector. When we resolve the R vector into Ry and this, so then this will be j cap and this can be some uxz cap. Correct? So then what you can, so this will be what? So this vector will be same as this vector. So you let us take this triangle. This will be what? Ry j cap. Correct? The same vector in a parallelogram. Right? So then, so your R vector will be Rxz uxz cap plus Ry j cap. Now let us take Rxz cap. So Rxz vector can be written as, so now you say, now we are resolving this, correct? So this will be what? We are resolving Rx I cap and this will be Rz k cap, ijk, correct? So now, so what will be this one? So this vector direction will be something like this and this vector something like this. So when I take, so I am taking a parallel vector drawing here. So this will be R, same thing na? Rz k cap. Now you see this. This vector direction is this vector direction is this vector direction is this. So Rxz vector using the triangle law here, am I right? This plus this will be equal to this. Correct? So what it will be? Tell me Rxz uxz cap, this is this vector, will be equal to this plus this. Remember, always you have to make sure about the direction. Because this is the direction like this, right? We are taking exactly equal vector. These are called as equal vectors, correct? Parallelogram, opposite. So equal vector. So this, you are drawing equal vector, so this direction also will be like this. And here, okay, so this will be what? Or x vector will be equal to this plus this, correct? So that will be Rx I cap plus Rz k cap. So when I substitute it here, what happened? So therefore, tell me now what this will be. R vector will be equal to R x I cap plus R y j cap plus R z k cap. Am I right? So this is the resolving of the vector. This is a basic. Now you got clear everything? Huh? So that's what our whole thing we are starting now. We have given a vector. We are going to resolve the vector into two vectors. That means what? That vector can be written as a sum of two vectors. That's what we are doing here. All clear? So now when I am resolving, when in a rectangular component, I am going to resolve the vector into two perpendicular vectors. Okay. So of course the sum will be same. Only then the magnitude case, your cos theta will go off. So only this thing will come up. Okay, fine. So what we are coming then? So I want to tell you this one. So now, given a vector, therefore you can call given a vector, any vector, a vector can be resolved in a three-dimensional space. X-axis, y-axis and z-axis. Or x, y, z, whatever you call. Usually when the people draw, there are x here, y here and z here. It's not necessary. Whatever the way you like, you can draw it. Okay, only thing they all should be perpendicular to each other. So any vector in space, this is important. Any vector in space, we are in a three dimension, correct? We are not ants moving on a board. We are, even though the surface is like a plane, we are moving on, but we can jump around. Okay, go on. So we are living in a three-dimension space. Okay, so we need three vectors, three dimensions. Okay, so what are the vectors? X, y and z. Okay, so any vector has to be resolved into x, y and z. As I told you, when you throw a stone, so you have to resolve in x and y to find out how much height it has reached as well as how much far it has reached. Given a velocity at a certain angle he is throwing. Okay, so similarly we have to do for all the problems, we need to resolve every vector into these three components. Along the I component, y component, j component and the k component. So any vector A can be resolved into ax I cap plus ay j cap plus az k cap. Okay, and this A vector can be any vector. It can be a force, it can be velocity, it can be acceleration. Remember that. So here what happened, we are not bothered about, in the whole calculations, we are not bothered about what is the physical quantity. All we are doing, if there is a physical quantity and if that physical quantity have a direction, how are we going to do our calculations? Okay, that's the whole approach of your vector algebra, vector algebra, whatever you call, vector operations and all. Okay, so and this is very important. And now if I have another vector, B vector, and if I am going to resolve this B vector also into ijk, x, y, z component. So what it will be? Bx I cap plus by j cap plus bz k cap. Now I am telling A vector equal to B vector. They both are equal. So then think of this image. A vector is equal to B vector. That means something same vector somewhere else. I am going the same way at some other axis I am going to draw. So and then if these two vectors has to be same, so then what about these components? Tell me. Will Ax be equal to Bx? Why? It won't be?
Because if it's saved, it will be. If it's saved, it will lie on the same position.
Okay, let us take. So we are going to draw. Okay, let me see it in two dimensions. Okay, let us see in two dimensions. In that case, then you will try to understand easily. So, what am I going to two dimension? Okay, let me give you a vector A. Resolve it into rectangular components. Then what am I going to do? I put in the tail, in the tail, I am going to draw perpendicular components. Am I right? So this will be x and this will be y. So what you are going to get is ax I cap and ay j cap. Okay, and suppose if you have this angle alpha or theta here, okay, so then we can find out what is ay and a cap and all you can find out, right? Now I am giving you another vector which is a b vector which is equal to a vector. So let me draw some else. B vector. Okay, equal vector means what? That direction is same and the magnitude, length is also same. So let me resolve it into the same perpendicular component along x and y. Because my x is defined. Am I right? I'm defining same cap, I cap, j cap, j cap. Now you can tell me, okay, I'm going to resolve it like this. So I have to resolve it like this. So now you want perpendicular now. Why do you want to resolve it like this? I can resolve it like this also. Am I right? But that is not allowed. Why that's not allowed? When I resolve it, if I call this as x, then this is not the same direction as this. You got it? Because remember, I am going to resolve it in the same direction. I cap, j cap, j cap, k cap, k cap. So you have to resolve it in the same direction. So that's why this is not allowed. So what we have to do is, so given a equal vector b, okay, and if I want to resolve into rectangular component as I cap, j cap and k cap, then this all has to be, I cap should be parallel to x here. Correct? And your j cap has to be parallel to y here. Am I right? So this is I cap, this is your j cap, and whatever, this is x or whatever. Okay. Now you tell me, so we have this angle has to be same, the same angle, like equal vector. So you are having bx, by. Tell me, will bx and ax be equal? This length and this length are same. This angle and this angle are same. Will this length and this length be same?
Yes.
Correct? Because what? This is what? This is a bx is what? Bx will be, okay, let me write it down. Correct. Bx will be equal to b cos theta. And ax will be a cos theta. Theta is same. A is equal to b. Of course, they both will be same. So therefore, and similarly, you can do it for 3 dimension also. I'm not going into it. So two vectors, remember, important thing is the two vectors are said to be equal when their resolved component along same directions. I cap, j cap, k cap, k cap. When the resolved components in all they have the same magnitude. Okay, so what we are saying, so if a vector is equal to b vector, what do we get is ax equal to bx, ay equal to by, and az equal to bz. So under these conditions only we can call the a vector and the means when these two vectors are equal, their corresponding xyz component also will be equal. Okay.